Okay, so let's start. All right, so okay. Okay. All right. So last time uh, we talked about the manifold structure on the tangent bundle of a smooth manifold. So the tangent bundle was a smooth manifold of dimension 2n, where n was the dimension of the manifold M. And then a vector field on an open subset U of M was a smooth map from the open subset U to the tangent bundle, such that for every point P, the vector tangent vector x at P belong to the tangent space TPM. Okay, so at each point P, you're choosing a vector in that tangent space. And since on a chart, we know that at each point we have a basis of the tangent space given by the tangent vectors del del xi. That means that at each point, x will become a linear combination of the del del xi, summation ai del del xi, where the coefficients are functions of the point. So the coefficients are going to be smooth functions if and only if x is a smooth map, right? Because that's how the manifold structure on the tangent bundle was defined, right? So if I compose with a chart on the tangent bundle, what was my chart on the tangent bundle? Capital phi. It sent a pair P comma a tangent vector at P summation ai del del xi at P. This went to phi of P comma a1 to an, right? So if x is a smooth map to the tangent bundle Tm, that means by definition that this chart phi, capital phi composed with x, that is a smooth map into R2n. And what are the coordinates of capital phi composed with x? They will be phi of P together with a1 of P up to an of P. So phi is already smooth. Phi is a chart on M. So this composition will be smooth if and only if a1 of P up to an of P are smooth. Is this clear? Okay. So x as a map into the tangent bundle is smooth if and only if the coefficients of x with respect to any local basis del del xi, the coefficients are smooth functions. Okay. So then we define chi of u to be the space of smooth vector fields on U. So we can add vector fields pointwise and take scalar multiples pointwise. So this forms an infinite dimensional vector space, okay, of vector fields on U. And then like we did in Rn, we can talk about an integral curve of the vector field. Yeah, any question? Okay, so a curve gamma, a smooth curve gamma in M is said to be an integral curve of the vector field x if it satisfies the differential equation gamma prime t is equal to x of gamma t. So notice we've defined for any curve gamma, its tangent vector at a point at time t, gamma prime t. We define this as an element of the tangent space at gamma t, right? So the left-hand side is a tangent vector in gamma at gamma t. And the right-hand side is also a tangent vector at gamma t, right? Because x of gamma t, by definition, will be a tangent vector at gamma t. So this equation makes sense. Both left and right-hand sides are tangent vectors at gamma t. And what we're saying is that at each point on the curve, the velocity vector at that point should be given by the vector field at that point, right? So for example, on the sphere, you could have a vector field which looks like this. For which the integral curves will be latitudes. Okay. And the vector field, if you want it to be continuous, you can see that at the north and south pole, it has to vanish. If you want it to be smooth everywhere, it has to vanish at the north and south pole, right? Because if I look in a neighborhood here of the north pole, in a chart, what will my vector field look like? In a chart, this looks like a disk in R2, and the vector field is going around in circles around the center of that disk, right? So if you want the vector field to be continuous at the center of this disk, then its length has to go to 0, right? As you converge to the origin. Is that clear? Yeah. Okay. So this vector field has to have 2 zeros at the north and south pole. So notice if you have a 0 of a vector field, if x of p is equal to 0, then that implies that the constant curve gamma of t constant equal to p is an integral curve, right? Because gamma prime t is identically 0 and x of gamma t is also identically 0, right? This is 0 and this is also 0. Okay.
But if Sn with n odd, then we can have a non-zero continuous tangent vector.
Absolutely correct. Yes, correct. That's right. So on S3, you can have a non-zero vector field everywhere. But on S2, any vector field has to vanish somewhere. Any continuous vector field has to vanish somewhere. Correct. Yes. Oh. Any more questions or comments? Okay, fine. So let's just see that like in Rn, we have local existence and uniqueness of integral curves of a vector field. This actually follows from the corresponding theorem for Rn, because if we look in a chart, then this equation gamma prime t equal to x of gamma t, this will reduce to an ODE in Rn. Okay. So let's just see quickly how to do that. So suppose phi equal to x1 to xn is a chart near a point gamma t naught. Okay, in some open set U. So let's look at the composition of this chart phi with gamma. So that will give me a curve gamma tilde in Rn. Okay. So say gamma tilde of t, this has coordinates x1 of t up to xn of t. Okay. So first of all, using this, I can work out what is this gamma prime t, what is the expansion of this with respect to the basis del del xi. So how do we do that? Well, we look at the action of gamma prime t acting on a function, a germ of smooth function near gamma t, right? So by definition, what is gamma prime t acting on f? It is ddt of f of gamma t. And this we write now as f composed with phi inverse, composed with phi composed with gamma t. So f composed with phi inverse, let me call that f tilde. And phi composed with gamma is gamma tilde. So now f tilde is a function on Rn and gamma tilde is a curve in Rn. So we can apply the chain rule for maps in Rn. So this will become the derivative of f. So that's a row vector, del f tilde del xi applied to gamma tilde prime t. That's a column vector. So this will become summation over I del f tilde del xi of gamma tilde t into the derivative of gamma tilde will be x1 prime t up to xn prime t. So here you'll get an xi prime t. And what is del f tilde del xi? This by definition is del del xi applied to f, right? So this sum I can write as the tangent vector sum over I xi prime t into del del xi at gamma t applied to f. Okay, so this is true for any germ of smooth function f. That means that gamma prime t is equal to sum over I xi prime t del del xi. Okay. So now this differential equation gamma prime equal to x of gamma, this becomes summation xi prime t del del xi equal to sum over, so x has coefficients ai with respect to the basis del del xi. So this becomes sum over I ai of gamma t del del xi. Okay. So let me reduce things to Rn. So the ai's are functions on the manifold in the chart. So to get functions on Rn, you look at ai composed with phi inverse. So that's a function ai tilde in Rn. So this, if I put a phi inverse and a phi in between, this becomes summation ai tilde gamma tilde into del del xi. So since the del del xi's are a basis, now these coefficients have to be equal, right? So that means I get n ODEs, xi prime, I get a system of ODEs, xi prime t equal to ai tilde of gamma tilde t, right? So that I can write as one ODE in Rn, ddt of gamma tilde, right, is equal to x tilde of gamma tilde t, where x tilde is the vector field on Rn with coefficients a1 tilde up to an tilde. Is this clear? Yes? Okay. So we've reduced our ODE on the manifold to locally in a chart, it's given by an ODE in Rn. Is this clear?
Yeah.
Okay. So now the local existence uniqueness theorem for smooth ODEs in Rn, this implies local existence and uniqueness of integral curves, right? That means that given any initial condition, gamma t naught equal to p, there exists for some time epsilon a unique solution defined on the interval minus epsilon to epsilon, or well, t naught minus epsilon to t naught plus epsilon gamma, which is an integral curve satisfying gamma t naught equal to p. Okay. So for every point you have a locally defined unique integral curve. Okay. And once you have local integral curves, then there's some abstract nonsense you can do to show that you have what are called maximal integral curves. So first of all, an integral curve gamma on an interval I in R into M is maximal if there does not exist a strictly proper extension of gamma. So that means an integral curve gamma tilde on an interval J such that J strictly contains I and gamma tilde restricted to I is equal to gamma. Okay. So gamma is maximal if it does not admit an extension, a strictly proper extension by another integral curve, gamma tilde. Okay. And then you can show using just the local existence uniqueness theorem that for any point P and N, there exists a unique maximal integral curve, gamma sub P, from an interval I sub P and R, okay, a unique interval I sub P and R into M, such that 0 belongs to this interval I sub P and gamma P of 0 is equal to P, okay. So once you have these integral curves, then like we did in Rn, we can define the flow of a vector field. So this is just a local flow in general. So given a point P naught in M, there exists an epsilon positive and a neighborhood U of P naught such that all the integral curves gamma P for P in this neighborhood U are all defined on a fixed interval minus epsilon to epsilon. Okay, so locally the existence time of the integral curves is uniform. That is, it's uniformly bounded below. Okay. This follows from the local existence uniqueness theorem for ODEs in Rn. Okay. So you have this common interval of definition for integral curve starting at points P and U, then we can define for mod T less than this epsilon, we can define as we did in Rn, the flow maps phi T. So this will go from the subset U in M into M. P goes to gamma P of T, right? So you start at P at time 0, and then you flow along the integral curve starting at P. You flow along it for time T. All right, so that gives you your flow phi T. So for example, here, in this example, the flow of this vector field, what would the flow be? What would the flow of this vector field be? So it will move along latitudes, right? So it will just be a rotation by some angle, say 2 pi t, along the north-south axis, right? Okay. Or if you normalize the vector field, then say it will be just rotation by t around the north-south axis. Is this clear? Okay, so this will be a map from S2 to S2. And you'll have a one parameter family of such maps. Okay. And just like in Rn, we have the semi-group property. If I take a neighborhood of an open set contained in U, whose closure is compact and contained in U. So on U, we have the flow defined. And now I'm taking a small, a compact set contained inside U. Then for S and T small enough, on V, on this set V contained in U, we will have the semi-group property phi T composed with phi S is equal to phi T plus S. Okay. Just like in Rn. And similar, and this implies that phi T composed with phi minus T, this will be phi 0. And phi 0 from the definition is the identity map, right? It's just P goes to gamma P of 0. Gamma P of 0 by definition is P, right? So you don't flow at all. You just stay where you are. Okay. So that means that the inverse of phi T is phi minus T. And from the existence uniqueness theorem for ODEs in Rn, these maps phi T are smooth. Okay, so phi T and phi minus T are smooth inverses of each other. So the maps phi T are diffeomorphisms. Okay. All right. Any questions?
We can do this not only for neighborhoods of P naught, right? We can like define the set of all points where
yeah, well, see, for a compact manifold, as I'm going to say just now, there's no problem. You can define the flow for all time. So let's make a definition. So a vector field X on M is complete if this interval of maximal interval of definition I sub P is the whole real line for all P in M. Okay. So all integral curves are defined for all time. Then we say the vector field is complete. And what one can show, it's not hard to show, is that if M is a compact manifold without boundary, then any vector field on M is complete. Okay. So on a compact manifold, there's no problem. The integral curves are defined for all time. On non-compact manifolds, you have to be careful because solutions to the ODE can, what they say, blow up in finite time. That is, they can escape to infinity in finite time. They may not be defined for all time. Okay. Escape to infinity means the solution leaves every compact set for T large enough. Okay. Sorry, for, well, T close enough to some explosion time T naught. Sorry. Yeah. There may be a finite explosion time T naught. And as T tends to T naught, you leave every compact set in the manifold. So anyway, let's not worry about that. So in most cases, we'll be looking at compact manifolds. So they're all vector fields. The flow is defined for all time. Anyway, for most of the properties of vector fields that we'll be needing, we will only need the local flow. Okay, we won't need the long-term flow in most of the cases. The local flow will be good enough for us. So now let me come to a very important operation on vector fields, which is called the Lie bracket. Okay, so we're going to define this purely algebraically, but I'll try to give a geometric interpretation of this Lie bracket later. So first, let's do the algebra. Okay, how do these arise algebraically? So first of all, the point is that vector fields can be interpreted purely algebraically using the ring of smooth functions C infinity n. So actually, given any ring, you can define what are called derivations of the ring R. Okay, this is a purely algebraic notion. I mean, you can do this over any field actually. So suppose you have a K algebra. Okay. So that means a vector space over the field K, which is also a ring with a ring multiplication, which commutes with scalar multiplication. Okay. So what is a derivation of a K algebra R is a K linear map D from R to R. So it's a linear map which satisfies the Leibniz rule. Okay. So the Leibniz rule is the usual product rule. D of F times G is equal to dF into G. This is the product in the ring plus F into dG. Okay. Yeah. So for example, you can take D to be ddx going from kx to itself. Okay. So here, this is just the formal derivative acting on polynomials, right? So that ddx of x to the power n is nx to the n minus 1, right? That defines your map on the basis, and then by linearity, it extends uniquely to the whole vector space of polynomials. Okay. Right. Or yeah, so more generally, you can take something like, if you want a very general form, you can take something like sum over I pi of x1 to xn del xi. This will act on polynomials in n variables k x1 to xn to itself. Okay. Is it clear? Yes. So these will be derivations. So what are they? They are, if you want to think in terms of analysis, they're first order differential operators, right? They're first order differential operators. Is that clear?
Yeah.
Yeah. If you have higher order terms like a second derivative del xi squared, it will not satisfy the Leibniz rule. It will, yeah, it will. So you can show that actually any derivation from kx1 to xn of kx1 to xn is of this form for some polynomials pi. Okay. Any derivation has to be of this form. So that's an exercise. You can prove that as an exercise. Okay. All right. So the point is that for a manifold, if I take any vector field x, then this defines a derivation of the ring C infinity n, of the algebra C infinity n. So let me call that derivation d sub x. So how is d sub x defined? So d sub x acting on a function f this is going to be another function, right? In C infinity M. What is its value at P? Well, it's very simple. You take X at P. So this is a tangent vector at P. Now F is a function on M. So I can look at its germ at the point P. And then you let this tangent vector act on this germ of smooth function at P, right? So that gives me a real number. So that is the value of dxf at the point P. Okay. All right. And then because X sub P satisfies the Leibniz rule at P, that means that this D sub X will satisfy the global Leibniz rule. Okay. So this will be a derivation of C infinity M. Is this clear? Yeah. So this gives us a map from the space of vector fields on M, chi M, to the vector space of derivations of C infinity M. Okay. Notice that derivations of C infinity M is also a vector space because the sum and scalar multiples of derivations will be derivations, right? Okay. All right. So this is the linear map. X goes to the derivation D sub X. This is in fact one-to-one and onto. This is in fact an isomorphism. Okay, so that's what I meant when I said that vector fields on M, you can recover them purely algebraically as derivations of the ring or the algebra C infinity M. Okay. So let's just quickly see that this is, say, one-to-one and onto, right? So for one-to-one, suppose that the derivation corresponding to a vector field X is identically 0. So D sub X is identically 0. So then given a point P in M and x1 to xn are coordinates near P. So these are smooth functions defined in a neighborhood of P. Now you can multiply them by a bump function supported near P, right? Whose support is contained inside the chart here where the xi's are defined. So that the product then becomes global functions on M, right? Phi times xi, where phi is your bump function, will become a smooth function on all of M. So you can extend them to all of M, right? They'll have compact support contained in a neighborhood of P. So you extend x1 to xn to functions x1 tilde to xn tilde, so that the xi tildes are equal to xi in a neighborhood of P, right? So you can do this by choosing your bump function equal to 1 in a small neighborhood of P. Okay. And then the germs of the xi tildes are the same as the germs of xi's, right? At P, because they're equal in a neighborhood of P. So therefore, x sub P acting on xi, this will be the same as x sub P acting on xi tilde. But now the xi tildes are global functions. So for a global function xi tilde, x sub P acting on this global function by definition is our derivation D sub X acting on xi tilde. But D sub X is given to be 0. So D sub X acting on xi tilde is 0. Okay. So xp acting on any coordinate function xi is 0. And then we have the representation of any tangent vector. X sub P is equal to sum over I, xp of xi del del xi. So xp of xi is 0 for all I. So this tangent vector xp is 0. Okay, this is true for any point P and M. So that means the vector field X is identically 0. Okay. So if the derivation is 0, then X is 0. That means that this linear map is one-to-one. Its kernel is trivial. And for onto, we can construct an explicit inverse to this map. So given a derivation of C infinity M, we can define a vector field X super D on M. So how do we define this vector field? So this vector field X super D at a point P. So this is a tangent vector. We have to define this tangent vector at P. So this has to act on germs of smooth functions at P, right? So acting on a germ of smooth function F, what can we do? Well, the natural thing is you extend F to a global function, right? On all of M. And then you let your derivation D act on that global function, right? So, so that's how we define this X super D at P acting on F. This is defined to be D acting on F tilde, evaluated at P, where F tilde is any global function whose germ is equal to the germ of f at P. Okay. So it's any extension of f to a smooth function on M. Now, all you have to check is that this is well defined, independent of the choice of extension to a global function, right? So why is that true? Because if I take two extensions, let's say, of this germ f to global functions, let's say f tilde, g tilde, so then f tilde and g tilde have the same germ at P. They're equal in a neighborhood of P. So what you can do is you can choose a bump function phi, which is constant equal to 1 in a very small neighborhood of P, and which vanishes outside a small neighborhood where f tilde and g tilde are equal. Okay. So then if I look at the function phi times f tilde minus g tilde, this will be identically 0. Right? Because if I'm in a small enough neighborhood of P, then f tilde minus g tilde is identically 0. And outside that small neighborhood, I've chosen phi so that it vanishes outside that neighborhood. So, so this product will be 0 outside that neighborhood as well. So this will be identically 0. Okay. So this is a global function which is identically 0. All right. So then that means since my derivation D is a linear map, D will map this 0 function to 0. So 0 is equal to D of phi times f tilde minus g tilde evaluated at P. And now we use the Leibniz rule. This is going to be d phi. So D is a derivation. So we use the Leibniz rule. This is d phi evaluated at P into f tilde minus g tilde at P. That is equal to 0. Okay, so the first term vanishes. And the second term, it will be phi of P into d of f tilde minus g tilde at P. So the phi of P is 1. So I'll get 1 times d of f tilde minus g tilde at P. So this is equal to 0. That means d of f tilde at P is equal to d of g tilde at P. So therefore, this vector field X super D, this is well defined. Is that clear? Yes?
Yes, it's clear.
Okay. So now, so now we have a map going in the opposite direction, a linear map, going from derivations of C infinity M to vector fields on M. So it's easy to see now that these two maps, phi and psi, these are inverses of each other. Okay, so let's just see that quickly. So, so if I take X to be the vector field, psi of D, right, then what is the derivation corresponding to X? So D sub X acting on a global function F at the point P. This by definition is X at the point P acting on F. And what is X at the point P acting on F? It's just abstract nonsense. You go through the definitions. This is by definition D acting on F evaluated at P, because F is a global function. So, right. So F already has a global extension. So this is by definition D acting on F at P. So that means D is equal to the derivation corresponding to X. Okay. All right. So in other words, psi composed with phi is, or what is it? So no, phi composed with psi is identity. That's what we've proved. Yeah. So that means that phi is onto, right? So therefore, this map is an isomorphism. Is that okay? Yeah.
Yeah. So
fine. Okay. So yeah. So we have less than a minute. Let me not say any more now. Any questions? We just have a minute left, so I'm not going to say any more now. We'll have to start the next session. Okay. So yeah, the point of this is that vector fields are can be viewed as purely algebraic objects, derivations of C infinity M. Okay. Okay, so let me stop this session and start another one. Okay.
So
Yeah,
we
go ahead.
So we have not used smooth vector fields, right?
No, we have used smooth vector fields. Absolutely. Smooth vector fields. When I say chi-m, I mean only smooth vector fields. Yeah.
So you should
We
check
have
that
used-
the inverse is also smooth, right?
Yeah, that's not hard to see. Yeah, that's not hard to see. You do that as an exercise. I mean, yeah. Sure. The vector field corresponding to a derivation is a smooth vector field. You just apply it to coordinate functions, global extensions of local coordinate functions.
Okay.
Those are smooth functions, and that's it. Those x applied to xi. Those. Okay. Yeah. So. Right. So I don't know who was asking, but someone was saying that, given a derivation, you get a vector field, right? Why is that vector field smooth, right? This is the question. Yes.
Yeah.
Right. So what are the coefficients of the vector field? The coefficients are x applied to the coordinate functions xi, right? Yes. Right. Yes. Who was asking?
Yeah. It's me.
Yeah, I don't know who. I can't see who the participant is. So anyway, whoever you are, the coefficients of the vector field are just the vector field applied to coordinate functions, right?
Yeah.
So what is the vector field applied to coordinate functions? By definition, it means you extend these coordinate functions to global functions like we did here, xi tildes. Then you apply your derivation to the global extensions, right? So the derivation applied to the global extension, those are smooth functions, right? So therefore, the coefficients of x are smooth. Okay. So the point is that your derivation is going from smooth functions to smooth functions.
Yeah. Makes sense.
Makes sense? Yeah. Now it's all right. Okay. So let's continue then. Okay. So why do we want to do this algebraic business? Because here's again a purely algebraic fact that if you take derivations of any K algebra, this is again, K could be any field here. If I take der of K, so if I take xy, our derivations of a K algebra are, then this is easy to check algebra. It's just an algebraic computation that if I look at x composed with y, so this means composition of linear maps minus the linear map y composed with x. Okay. So this will also go from R to R, right? So this linear map, this will also satisfy the Leibniz rule. Okay, so this will also be a derivation of R. Okay, and this xy minus yx, this is defined to be the Lie bracket of x and y. Oh, okay, this is a definition. It's x composed y minus y composed x. Okay. Yeah. So it's easy to see that you just do this x composed y applied to a product f times g minus y composed x applied to f times g. You'll see that a bunch of terms cancel and you'll be left with a Leibniz rule for this. Okay, this satisfies the Leibniz rule. So I'm not going to do that. You can just do that computation. It's very simple. Okay. All right. So analytically, what is happening? If you look at this example of first order differential operators, what will happen is that when I look at x composed with y, so x and y are both first order differential operators, the composition will be a second order differential operator, and so will y composed x. These will both be second order differential operators, but their second order terms are equal. And that is because the second order terms will have second order partial derivatives and those commute. Okay. So that will lead to the second order terms cancelling here. this X composed Y and Y composed X, they will have the same second order terms. So what will remain are just first order terms. Okay. You can think of it that way, if you like. All right. So you'll get a difference of two second order differential operators is a first order differential operator. Hence, it is a vector field or a derivation. Okay. All right. So this is a purely algebraic fact. So what that means is that actually there's derivations of R. R is any K algebra. Together with this bracket operation, this is what is called a Lie algebra. It's a purely algebraic structure. So we won't be needing D algebras in this course. So I'm not going to write down the definition. I'll just say it in words. This Lie bracket is a bilinear product, right? From this vector space cross vector space to itself. It's a bilinear product on the vector space, which is anti-commutative. That's easy to see. Bracket of xy is minus the bracket of yx, right? That's clear from the definition. And it satisfies the Jacobi identity. Okay, so if I take, so I'm sure you've probably all seen the Jacobi identity. I'm not going to write it down, okay? That's something you can check. It holds for, when you have three vector fields, you get an identity which holds when you add up brackets of cyclic permutations of the three vector fields, okay? So that is a Lie algebra, okay? So bilinear product, which is anti-commutative and satisfies Jacobi identity. Okay. So the derivations has this extra structure of a Lie algebra. Okay. And that now, by identifying derivations of C infinity M with vector fields on N, that will give us a Lie algebra structure on the space of vector fields on N. Okay. So given X, so first of all, this is a notation. We will be using this notation frequently. You write XF for the function given by the vector field acting on F pointwise. In other words, the derivation d sub x acting on F. Okay. This is again a smooth function on N. Okay. So XF will be this smooth function on N. Okay. So now, given vector fields xy, you define their Lie bracket. This is a typo. This should be chi m, not C infinity M. So xy is an element of chi m, another vector field. So to define the vector field, it's enough to define the corresponding derivation, right? Since that is equivalent data. So this derivation bracket xy acting on F is x acting on y acting on F minus y acting on x acting on F. Okay. So this xy minus yx, this is a derivation of C infinity M. Okay. So this is a purely algebraic definition of the Lie bracket of two vector fields. All right. And if you like more algebraic things, then it's fine. But I'll try and give a more geometric interpretation of this in a while. All right. But is the definition clear of the Lie bracket of two vector fields? You take the corresponding derivations, take their Lie bracket, that is a derivation. Hence, it defines a vector field, okay? Which is defined to be the Lie bracket of xy. Okay, is the definition clear? Any questions? Okay. All right. So now some more basic definitions. So we haven't defined derivatives of smooth functions on a manifold and smooth maps between manifolds. So those are going to be linear maps, but now they will be linear maps between tangent spaces. Okay, for functions on Rn, the derivative was a linear map from Rn to R. And for functions from Rn to Rm, the derivative was a linear map from Rn to Rm. But now from a function on a manifold, so suppose if f is a smooth function on an open set U in N, then for any point P in U, we can define the derivative df at P this is now going to be a linear map from the tangent space TPM to R. And the definition is canonical. You take a tangent vector V at P. So V acts on germs of smooth functions at P. So you let V act on F. Okay. So you get the linear map, V goes to V of F. This is going from TPM to R. Okay. This by definition is the derivative dF at P. Okay. So this is a linear functional, okay, on the tangent space. Okay. Now suppose phi from M to N is a smooth map. Then we want to define the derivative d phi at P. This is going to be a linear map between tangent spaces from the tangent space at P, TPM, to the tangent space at phi of P in N. Okay. So what is this? So I have to define for any tangent vector V, I have to define a tangent vector at phi of P. So let's say W. So W is supposed to act on germs of smooth functions, say G defined near phi of P. So suppose I take G as a germ of smooth function defined near phi of P, then I can compose G with phi, right? To give me a germ of smooth function defined near P. Okay, so G composed phi will be defined near P. So then V will act on G composed phi, right? So that will give me a linear map from germs of smooth functions near phi P to R, right? G goes to V of G composed phi. Okay, so this will be my tangent vector W. Okay, this will satisfy the Leibniz rule at P because at phi of P because V satisfies the Leibniz rule at P. Is that clear?
Yeah, it's clear. Yeah.
Okay. So now we have, like we had in Euclidean spaces, we have the chain rule. So if you compose, let's say, a smooth map between manifolds, you compose with that with a smooth function mapping into R. Then you'll have, these are easy to check. I won't do this. The derivative of the composition F composed phi at P will be dF at phi P composed with d phi at P. That will be a linear map from TPM to R. And similarly, if I have two smooth maps, then you have the chain rule. The derivative of psi composed phi at P will be d psi at phi P composed with d phi at P. Okay, so that will be a map between the appropriate tangent spaces. Okay, so these are easy to check. I leave it to you to check them. It's just abstract nonsense, so nothing happening there. Yeah. Okay. So yeah, let's talk briefly about push forward and pull back of vector fields. So maybe let me just draw a picture here that will be easier to understand. So suppose I have a diffeomorphism between manifolds. Okay, so that means a smooth map with a smooth inverse. Oh, what happened? Oh God. Yeah, okay. So suppose yeah, so say I have, this is one manifold. So it's topologically a sphere. And I have this diffeomorphism F, and I'm mapping it to a round sphere. Okay. And so suppose I had a vector field, say Y on the right-hand side in the range. Okay. So that's, say, the vector field we were looking at earlier on S2. Okay. Then I want to define the pullback, which will be, so F upper star Y. This will be a vector field on M. Okay, so this is my M, and this is my N. Okay. So how do I define this pullback? Well, you do the obvious thing. So, I mean, in the picture, you can see how to pull it back, I suppose, right? One way to do this in the picture is you just take the inverse image of these integral curves here. Those will give curves which are integral curves of a vector field here. And that vector field is the pullback. That's what we're doing in this picture, right? You're pulling back, in other words, taking the inverse image of these integral curves on the right-hand side, you get integral curves on the left-hand side. That defines a vector field. Okay. So you can do this using integral curves if you want, but infinitesimally, what are you doing? You're taking a point P here. Then you look at f of P here. So you have a tangent vector y at f of P, and you have the derivative. So because f is a diffeomorphism, so that means it has an inverse, right? G composed f is identity. So that means dg at fp composed with df at p. This will be the derivative of the identity at p. And it's easy to see the derivative of the identity at p is just the identity of TPM, right? So it follows that if f is a diffeomorphism, then at each point, its derivative is an isomorphism, right? So the derivative is an isomorphism from the tangent space here to the tangent space here. So I can take the inverse image, right, of this tangent vector to get a tangent vector here. Okay. So x at p then is defined to be, you take the derivative at p, take the inverse image under that isomorphism of y at f of p. Okay. So this will be a tangent vector at p. Is that clear? Yeah. So it's clear from the picture that f will map integral curves of x to integral curves of y, right? Okay. Okay, so, and similarly, we can define the push forward. So, okay, so I've defined the push forward here first. So that is f lower star x. So that will be a vector field on n. Given a vector field x in n, you can push it forward. So what is f lower star x at a point q in n? What you do is you take the inverse image of q. You look at x at the point f inverse of q, and then apply df at f inverse q. That will go forward and give you a tangent vector at q in n. Okay. And the pullback I've just defined previously, f upper star y at p will be dfp inverse of y at f of p. Okay. Fine. Okay. Now, we may not always be able to push forward or pull back if f is not a diffeomorphism. If it is just a smooth map, these may not be well defined because we're taking inverses. Okay, and those may not exist for either f or for its derivative. Okay. So you have to be a bit careful about push forward and pull back if f is not a diffeomorphism. So there is a more general notion of what are called f-related vector fields. So if f is a smooth map from m to n, and I take two vector fields x in m and y in n, then we say that x is f related to y, and that's written x tilde sub fy, if at each point p, the derivative df at p maps the vector x at p to the vector y at f of p. Okay. So if f is a diffeomorphism, then you can see from the definition, this just means that x is the pullback of y. And similarly, y is the push forward of x. Okay. But this is more general. F does not have to be a diffeomorphism. So let me give you a simple example. F could be a quotient map. What it means is that the vector fields are compatible with the quotienting. So suppose just the easiest example is you take a cylinder, S1 cross R. And let's say you take, you can take the horizontal vector field on this cylinder. That is your X. And then F you take to be the projection to a circle, to the circle component. Okay. So there you take just this vector field which goes around the circle. Okay. Then these two vector fields are F related, even though F is not a diffeomorphism. Okay. That means if I take any point here, then under the derivative, this tangent vector projects to the tangent vector below, at the point below. Is that clear? If this is P and this is F of P, okay, then X is F related to Y. Okay. And in fact, it's easy to see that because this map pi, this projection map, it sends each vertical line here to a point, right? That means the derivative is going to map vectors tangent to this line to 0 below, right? Okay. So in fact, if I take any vector field on the cylinder, which is this horizontal vector field plus some vertical vector field, which is tangent to the vertical lines. Okay. So maybe the integral curves will look something like this. They could spiral around the cylinder, something like this. Okay. This will still be F related to Y, to the vector field Y below. Do you see that? So if I add some vertical component, this will also be F related to Y. Can you see that? Yeah. Because dF is going to kill the vertical part. Okay. Is that clear? Yeah.
Yeah.
So what does it mean actually? I mean, dynamically in dynamic terms for F related vector fields? Well, the answer is given in the next proposition, I think. So the following are equivalent. X is F related to Y, and 2, F composed with the flow of X is equal to the flow of Y composed with F. Okay. So what does this property mean? This means that the flows are what we call semi-conjugate. Okay, in the terminology of dynamical systems, that means that so if I flow, so the flow of X goes around these horizontal circles, right? So here I have, say, phi tx from M to N, and here I have F from M to N, and here I have phi ty, right? Then this diagram commutes. So that means that flowing by X, okay, so if you flow above here, so I'll flow up like this, and then I project, is the same as first projecting and then flowing below, right? Is that clear?
Yeah, it's clear.
Okay, so I mean, it's just this picture, right? I mean, I don't know how better to say it. So look, it's this picture. So if I start here and I flow first and then I project, okay, I'll come here. That's the same as first projecting and then flowing, right? This diagram commutes. Is that clear? Yep. Okay. So the flows are semi-conjugate. In other words, you can think of the dynamical system below as a quotient of the dynamical system above. All right. So so in categorical terms, I mean, the flow below is a quotient of the flow above. Okay. The system below is a quotient of the system above. Okay. If F is a diffeomorphism, then they are conjugate. So they're isomorphic in a sense. Okay. All right. But in general, they're just semi-conjugate. So the flow below is a quotient of the flow above. All right. You lose some information when you quotient. All right. Is this okay? Yeah. And the third property, which is equivalent to being F related, is that if I take any smooth function phi on n, then x applied to phi composed F is equal to y applied to phi and then composed with F. Okay. So I'm not going to prove this. You can prove this as an exercise. It's not very difficult. It's quite easy, except just the third equivalence needs a little thought, but I'll leave it to you. Try and do this as an exercise. So using property 3, we get an important property of the Lie bracket that if I have two vector fields, x1, x2 on n, and two vector fields y1, y2 on n, and say xi is f related to yi, okay, for all I, then the brackets are f related. So x1, x2 is f related to bracket y1, y2, okay? And that you can prove using this third property. So again, I'm not going to, you can just look at the proof. It's just a calculation, all right? You just verify that this third property holds using the definition of the bracket, the algebraic definition. Okay, fine. So why was I interested in F-related vector fields? Because I want to give a first more geometric interpretation of the Lie bracket in terms of what's called the Lie derivative of a vector field. Okay. All right. So the Lie derivative is the following. So suppose xy are vector fields on M and phi t is the local flow of x. Then I want to differentiate y in the direction of x. Okay. So let me draw the picture to explain what we are trying to do here. So suppose I have an integral curve of x, all right? So this is say P, and this is say phi t of P. Okay. So say phi t equal to, so here I'll just be using the local flow. I don't need a global flow here. So this is the local flow of some vector field x on M. Okay. And I take another field y on M. Okay. Then we want to differentiate y in the direction of x. Okay, so now if you think about this for a second, you'll realize there's a serious difficulty here. Why is that? Because if I take y at the point, so that would mean differentiating y along the integral curve of x, right? It means essentially you want to differentiate y along an integral curve of x, right? But what is the problem with that? The problem is if I look at 2 points on the same integral curve, say P and phi t of P. So here's y at P, and here is y at phi t of P. Well, the problem is what? Can anyone tell me what the problem is if I try to differentiate here? I want to subtract y at phi tp minus yp, right?
This is different points, right? I mean, at different tangent spaces.
Correct. They belong to different tangent spaces. And normally in a manifold, the tangent spaces, we do not have a canonical way of identifying different tangent spaces, right? We do not have a canonical way of identifying different tangent spaces. So a priori, it does not make sense to subtract yp from y at phi tp, right? This minus this doesn't make sense. They belong to different vector spaces. So what can we do? How can we rectify this? So I have the tangent space TPM here, and I have T phi TPM here, right? Now, so far we have not used the vector field X apart from this integral curve. Does X give us some extra data that we can use?
So we can pull back using phi t, I suppose, or push forward, whatever.
Correct.
And
So
to get this
in terms of tangent spaces, what can we do? Is there a natural map between the tangent spaces at P and phi TP?
phi t, I mean d phi t.
D phi t, correct. So D phi t at P, this will be a linear map from the tangent space at P to the tangent space at phi t of P, right? And because phi t's are diffeomorphisms, this linear map will be an isomorphism, right? Yes? This will be an isomorphism. Therefore, I can use this isomorphism to identify these two tangent spaces, right? After identification, then I can take their difference, then I can divide by t and let t tend to 0. Okay, then I get a derivative of x in the direction of x. So the point is we have to use the derivative of the flow to identify nearby tangent spaces at nearby points, right? So what will I do? I'll take the inverse of this derivative. So that will give me some tangent vector here now. And then I take the difference of these two, this difference, and then I divide by t and let t tend to 0. So what will this be? This vector here will be, running out of space, this will be, so what is the inverse of the derivative of phi t? Well, the inverse of phi t is phi minus t, right? So if phi t and phi minus t are inverses, then by the chain rule, their derivatives are inverses, right? So this map from this tangent space back to this one, this will be the derivative of phi minus t at the point phi t of P. Right? So I use that to map here. So what am I going to do? I'm going to look at y at phi t of P. Then I apply my isomorphism, that is d phi minus t at the point phi t of P applied to this y at phi tp. Now this is now a tangent vector at P. So from this I can subtract y at P. Now I can divide by t. And then what one can show is that this limit exists. So as t tends to 0, this converges to a tangent vector, which is called at P, which is called the lead derivative of y with respect to x at P. Okay, so this is in TP. Okay. So this is how one defines the Lie derivative. All right. Okay. So, so it's the limit t tends to 0, d phi minus t at phi t of P applied to y at phi tp minus y at p divided by t. Okay. And this expression, it's easy to see. This is ddt of the pullback phi t star y at p. Okay. So when I say ddt of this family of vectors, what I mean is this phi t star y, these are vector fields on M, right? In a neighborhood of P, let's say. Okay. The flow is local, fine. So in a neighborhood of P, these are vector fields. So in particular, each of these vector fields I can evaluate at P. So that gives me a curve in my tangent space, right? In a fixed tangent space, I take the derivative of that curve in the tangent space at time t equal to 0. Okay. So that gives me ddt at t equal to 0 of phi t star y at p. Is that clear? That is the same as this limit. Okay. So you can show this limit exists and gives you a smooth vector field. All right. And in fact, now we can even prove that this Lie derivative, Lxy, this is nothing but the Lie bracket. Okay. It's nothing but the Lie bracket. So I've written a proof here, but I want to skip ahead because I want to go a bit fast. So you can look at this proof. If you have any questions, you can ask me. It's not very difficult. So I'll just go ahead. Okay. So that's one interpretation of the bracket. I'll try and give you another one if we have time. I'll state another interpretation and leave it for you as an exercise to prove. So so once we know that the Lie derivative is the same as the Lie bracket, we can prove the following, that the following are equivalent. 1, the bracket of xy is 0. 2, x is phi t x related to y for all t. That means y is phi t related to y, where phi t is the flow of x. Okay. So the flow of x sends y to itself. Okay, the flow of x sends y to itself. And 3, the flows of x and y commute. Okay, so phi sy composed with phi tx is phi tx composed with phi sy for all st. Okay. So just look at this second property for a second. Remember from the previous proposition that if two vector fields are F related, this semi-conjugacy, what does this mean? This means that F of an integral curve, if I vary t here, I get an integral curve of x. That will give me an integral curve of y, right? If I vary t on the right-hand side, I'll get an integral curve of y, right? Passing through f of p. So that means F maps the integral curve of x passing through p to the integral curve of y passing through f of p. Is that clear? Yeah, that follows from this semi-conjugacy relation, right? Yes?
Yeah.
Right? Just put a p here and then vary t, right? Then on this side, you get f of the integral curve of passing through p. And on this side, you get the integral curve of y passing through f of p. Okay, that's it. So F maps integral curves of x to integral curves of y. All right. So in this case, the flow of x is going to map integral curves of y to integral curves of y. Okay. And yeah, if the bracket is 0. Okay, let me stop this session and start a new one. Okay. Okay. So all right. So, okay, so let me just, this proposition I can sketch the proof of. So it's given here. So I want to show 1 implies 2. So y being phi t x related to y, That means that if phi t is the flow of x, then phi t star y is equal to y, right? The pullback of y by phi t is equal to y, right? So, since the phi t's are diffeomorphisms, so I have to prove here that if bracket xy is 0, then phi t star y is equal to y for all t. So let's look at ddt of phi t star y at p. So this at time t, I can write this as dds at s equal to 0 of phi t plus s star of y, right? But phi t plus s, I can use the group property. This is phi t composed with phi s, right? And I can also write it as phi s composed with phi t. So when I take pullback, that will become phi t star composed with phi s star of y. And now t is fixed, s is varying here near 0. So this phi t star is a linear map. So I can pull it out of the derivative. This will become phi t star of dds at s equal to 0 of phi s star y at p. And this phi s star y, the derivative of this with respect to s at s equal to 0, this by definition is the Lie bracket, Lxy. Okay, so this is going to become phi t star of Lxy at p. Okay. And this is 0 because Lxy is equal to the Lie bracket, which we're assuming is 0. So that means that ddt of phi t star y, this is 0 for all t. So therefore, this is constant in t. So that means that phi t star y is equal to phi 0 star y. And phi 0 is the identity. So phi 0 star y is just equal to y. Okay, so this is true for all t. So phi t star y equals to y means exactly that y is phi t related to y. Okay. And the second property that the second and the third property that the flows commute, these two are equivalent. This follows from the fact that from the previous proposition that, x is f related to y if and only if f semi-conjugates the flows of x and y, right? So here, y is f related to y if and only if phi t y composed f is equal to f composed phi t y. So here for this f, you just take f equal to phi t x or phi s x, right? Then that will give you that, the flow of y composed with this f will become the flow of x is equal to flow of x composed with flow of y. So the flows commute, all right? Is that clear? Yeah.
Yeah.
Okay. And finally, if y is phi t related to y for all t, then the Lie bracket becomes 0 because the Lie bracket is the Lie derivative, and the Lie derivative is ddt at t equal to 0 of phi t star y. And this is 0 because we're assuming phi t star y is equal to y for all t. So this is constant in t, so its derivative is 0. Okay. Is that clear? Yeah. Okay. All right. So before passing on, let me now give a last geometric interpretation of the Lie bracket. So this is fairly geometric. You can view the Lie bracket as the Lie derivative, which is pretty geometric. But since vanishing of the Lie bracket corresponds to commuting of the flows, so it would be nice to have an interpretation of the Lie bracket in terms of commutator of the flows, right? So that we can do, in fact. So as follows. So Lie bracket. This can be viewed as an infinitesimal commutator of the flows of x and y. So what you do is you take a point P. So now the Lie bracket is a tangent vector at P, right? So how do I get this tangent vector? Well, you can do the following. You flow along an integral curve of x starting from P for a small time t. Okay. So you come to say, okay, the notation, I mean, it's just going to get a bit messy, but let me, so yeah. So you flow in the direction of x, then you flow in the direction of y, then you flow in the direction of minus x like this, and then you flow in the direction of minus y. Okay. So if you do all of these for time t, okay. So this will be, so if the, say, phi t equal to flow of x and say psi t equal to flow of y, so then this will be phi t p, and this will be psi t of phi t of p, and this will be phi minus t psi t phi t p, and this last point here will be psi minus t phi minus t psi t phi t of p. So this last point, this is a commutator, right? This is psi t inverse, phi t inverse, psi t phi t, right? Okay, this is a commutator. Yeah. So the bracket is basically the vector which points in this direction. So if the flows commuted, right? If the flows commuted, then this quadrilateral would close up, right? You would come back to P. Okay, and the bracket would be 0. But in general, this little quadrilateral, it does not close up. Okay. And you get a little displacement here from P to a nearby point. So what happens is, if these are of length of order t, right? Because you're flowing for time t. These are of order t, order t, order t. This is of order t. Now what happens is, because I'm flowing by x here, y, and then minus x, and then minus y, the x and the minus x and the y and the minus y, up to first order, they cancel out. Okay, up to first order, they cancel out. What remains is a second order term. So this thing here, this little displacement here, this will be of order t squared. And in fact, if I look in a chart, then these 2 points in Rn, the difference between these 2 points in a chart, it will be the bracket of xy at P into t squared plus little o of t squared. Okay. So the bracket is this little difference that comes up here. So if you want to express this without charts, so if we're in Rn, okay, so if we are in Rn, we can give an exact formula for the bracket as follows. So in Rn, bracket of xy at P is equal to the limit t tending to 0, psi minus t, phi minus t, psi t, phi t, p minus p divided by t squared. Okay. This is the bracket in Rn. Okay. So this will give you a vector in Rn. Okay. So look, in Rn, it makes sense to take the difference of these 2 points, right? Now, in a general manifold, we can't take this point minus this point. It doesn't make sense. We can do that in a chart. So in a chart, this formula will still be true. But if you want to do it without charts, then on M, what you can do is, if you take any function f, a smooth function, then, so remember the bracket is determined by how it acts on function. A vector field is determined by how it acts on functions. So the bracket of xy acting on f, okay, at P, right? So of course, this we know by definition, this is df at P acting on bracket of xy at P, right? Yes? Okay. This is going to be equal to the limit t tending to 0, f of psi minus t, phi minus t, psi t, phi t, p, minus f of p, okay, divided by t squared. All right. So I leave it to you to prove this last equality as an exercise. This is a good exercise. It takes some work to do this. So see if you can do this. Okay. So, you know, if you apply this to the coordinate functions, right, where f is equal to some coordinate function xi, then that tells you that, you know, xi of this point minus xi of p, this divided by t squared converges to the dxi acting on the bracket. In other words, the coefficient of bracket xy, you see what is bracket xy in terms of the basis del del xi, it's equal to sum over I bracket xy acting on the coordinate functions xi, right, into del del xi. Yes, we've used this formula before, right? Yeah. So this thing you can compute from star, from this equality. So let me call this star. Okay. This you can compute from here, right? Is this clear? Okay, putting f equal to xi. Is it clear?
Yeah.
Okay. All right. So does this interpretation of the bracket make sense? Yeah. So it is an infinitesimal commutator of the flows, right? You're measuring how far the flows are from identity, basically. The commutator is from identity. Okay. So, you know, if you want, you can write it in this following form that you know, if I write the flow as e to the tx, so then basically what you're saying is that e to the minus ty, e to the minus tx, e to the ty, e to the tx is equal to identity plus t squared bracket xy plus little o of t squared. Okay. That's what this means. All right.
I had a question.
Yes.
Why is the distance between P and phi TP big O of T?
Because you're flowing for time t, right?
Okay. Yeah.
I mean, it's just a gamma p of t, right? Gamma is a smooth curve.
Yeah.
So it's just gamma p of t that gamma is a smooth curve, so gamma in time t is going to move a distance big O of t, right? So,
Yeah, yeah, okay.
right. So that is just a smooth curve. So, yeah. Okay, so try and prove this exercise. It's a nice exercise. Okay. All right. Let me carry on now. So, okay, so that's enough about vector fields and Lie brackets. So now we can start finally on integration, okay, of differential forms. So again, we're going to go through this as fast as we can. So, okay, so we defined the tangent bundle. Similarly, we can define the cotangent bundle, T star M. So the tangent bundle was the disjoint union of tangent spaces TPM. So what you can do is for each tangent space TPM, you look at its dual, which we denote by TP star M. So this is the dual of the tangent space. And then take the disjoint union of these dual spaces, okay? So this is the cotangent bundle, T star M. And similarly, you can show this is also a manifold of dimension 2n, okay? And we can also do the following, which is look at pointwise the kth wedge product of TP star M. So remember what this kth wedge product of a dual space V star is. This is the space of alternating k multilinear functions on the tangent space. Okay. So at each point P, we're looking at the k multilinear functions on the alternating multilinear functions on the tangent space. Then I take the so these are vector spaces for each point P of dimension, the same dimension n choose k, and then I take the disjoint union of these. So it's not hard to show this also becomes a smooth manifold. In fact, both of these manifolds are examples of what are called in general vector bundles, okay, which means a collection of vector spaces of the same dimension parametrized by some topological space. Okay, that's informally what it is. We're going to talk about vector bundles in more detail after we finish talking about integration. That'll be the next topic, since we'll need to understand a bit vector bundles before we can get to harmonic maps. So these are informally vector bundles are just a collection of vector spaces parametrized by some base topological space, right? So here the base is M. And then over each point in M, you have either the tangent space or the cotangent space, which is the dual space, or this kth wedge product of the dual, okay? You can form various vector bundles over the same base space, right? By taking tensor products, wedge products, dual, etc. Okay. Okay. So, a vector field was a map where at each point you chose a vector in the corresponding vector space, right? The tangent space. So similarly, so that is what's called a section of the vector bundle. So we'll be talking about sections of vector bundles, but I'm just saying it in words right now. We'll talk about this in more detail soon. So similarly, at each point, you can choose an element of the cotangent space that will give you what's called a differential form of degree 1. And similarly, for any k, at each point, you can choose an element of this kth wedge of the cotangent space. Okay. So at each point, you will have an alternating k multilinear function on the tangent space. And that you want to vary in a smooth way, okay, with the point. So that will be a differential form of degree k. So this will be a smooth map from M to the kth wedge of the cotangent bundle. So that at each point P, omega at P is an element of wedge k TP star M, okay. So this might all seem sort of abstract. Concretely, what does it mean? So in local coordinates, say x1 to xn on a chart U, then we know the del xi's are a basis of TPM, right? Now we know the derivatives, the xi's are functions So their derivatives are linear functionals from TPM to R. So these are elements of the cotangent space, right? TP star M. These are dual elements of the dual. So what is this dual element acting on this basis vector? Well, dxi acting on del del xj, by definition of the derivative, this is the tangent vector del del xj acting on the function xi, right? And what is del del xj of xi is just delta ij, right? So that means that dxi acting on del del xj is delta ij. In other words, dxi is the dual basis of TP star M, right? Dual to this basis del del xi. Is that clear? Yes? Right. See, the dual, if EI is a basis of a vector space V, then the dual basis EI star of V star is characterized by this property only. EI star of EJ is equal to delta IJ, right? That's how one defines the dual basis. Yes? Is that clear? Yes, some response, anyone? Is it clear?
Yeah, yes, sir. It's clear.
That's fine. Okay, thank you. Okay, thank you. Okay, so we've defined what is a differential form. And that means at each point you're choosing an alternating K multilinear function on the tangent space. So again, differential forms you can add pointwise. Okay, so let omega Km be the space of smooth K forms on M. So now if omega is a differential form of degree K, then look, we saw that this wedge K of V star, right? We had a basis for it in terms of the dual basis of V star, sorry. If EI star was the basis of V star, the dual basis, then the basis of the kth wedge product was EI1 star wedge EIK star, right? Where I1 to IK are in strictly increasing order, right? So here my dual basis is DXI, right? So therefore, any so the k-fold wedge products of the DXIs in increasing order, that will give me a basis for this wedge K TP star M, right? So pointwise, any omega p will be a linear combination of dxi1 wedge dxik, where I1 to Ik are in strictly increasing order. Okay, with some coefficients a, I1, Ik. All right, where these, so I'm in compact notation, I'm just going to write this as sum over multi-indices I bar, a I bar, dx I bar, where dx I bar, so first I bar is this multi-index, I1 to Ik in increasing order. And dx I bar stands for dxi1 wedge up to dxik. Okay. Right. Is this all right? Yeah. These are linear functions, right? I can take their tensor product and their wedge product, right? Yes?
Yeah.
Okay, so this will be an alternating K multilinear function on each tangent space, right? Okay. Okay, so any differential form omega becomes summation ai bar dxi bar, okay? In local coordinates. So let's look at some simple examples. So suppose f is a smooth function, right? Then df is a one form, right? A differential form of degree 1, right? Because at each point it's a linear function on the tangent space. So what is its expression with respect to the basis dxi? So df at p, this I can write as sum over I, df at p ei into ei star, right? Yes? Yeah. Now what is my ei? Ei is del del xi. And what is ei star? This is dxi, right? So what will dfp of ei be? that will be DFP acting on del del xi. That by definition is del del xi acting on F, right? So, and this EI star is DXI. So this will become nothing but sum over I del F del xi into DXI. Okay. So DF is equal to sum over I del F del xi DXI. All right. Okay. So to talk about integration of differential forms, okay, so the idea is that a differential K form is a way of measuring infinitesimal K dimensional volumes. Okay. Why is that? I mean, because remember what the wedge product was. So dxi1 wedge dxik applied to vectors v1 to vk, right? This was a determinant, right, of some k by k matrix, right, where you had dxi1 up to dxik acting on v1 and then acting on vk, right? Right? Yes. Okay. So what does this mean? This means this is a k-dimensional volume, right? This is the k-dimensional signed volume. Signed because, I mean, this could be positive or negative, right? So of the map, dxi1 up to dxik, so image of v1 to vk under this map from TPM to RK, right? So let me just draw you a picture so this seems less abstract. So example, if let's say n is equal to 3, so 3 dimensions, and k is equal to 2. Okay, so if I have a 2 form in 3 dimensions, right? So then it's something of the form p dx, so omega is a 2 form in 3 dimensions. It's p dx wedge dy plus q dy wedge dz plus r dx wedge dz, right? Okay. So each of these dx wedge dy acting on 2 vectors vw, that will be a determinant of a 2 by 2 matrix, right? Now, what is that determinant? It's the following. So you take, let's say in your tangent space, which is 3-dimensional, right? So so what we're doing is, so say this is the this is the del x axis, this is the del y axis. These are your basis vectors. So we have corresponding axes, right? This is the del z axis. So if I take two vectors v and w, right? What we're doing is we're taking the parallelogram spanned by vw, right? And then we're projecting it onto, let's say, the xy plane. So that's one projection, right? So in the xy plane, I'll get one projection like this. Okay, so this is the projection to del xy, projection to del x, del y plane. Okay, so here you take the projection, then you take the area of the projection, and then you multiply by p. That will give you the first term. Is it clear? Similarly, for the other terms, you take, so you have one projection like this, then you have another projection to the span of del y and del z, something like this. Okay, so this will be the projection to del y, del z plane. Okay. So here you take the area of this projection and multiply by q. Okay. So you take area of this projection and then signed area into p. And then here you'll take area of this projection into q. And similarly, you'll have another projection, which I can't draw. It's the del x, del z plane, which is this vertical plane coming parallel to the board, right? So you'll take that projection, multiply by r. Then you add up these areas times these coefficients, p, q, r. That gives you omega of VW. Is it clear? Yeah. Yes.
Yeah, it's clear.
Okay, so that's what this differential form acting on k vectors is. You basically take projections to the subspaces spanned by the k basis vectors, right? Then in that, you get some k-dimensional parallelepiped in a k-dimensional space, right? There you take its k-dimensional signed volume, then you multiply by the coefficient a I1 to ik, and then you add up those k-dimensional volumes, right? So if you are doing physics, then this would come with a, you know, I mean, it would come with units of meter to the power k, right? They're volumes. They're k-dimensional volumes. Okay. Is this clear? Yeah. Okay. Right. A determinant is a volume after all, right? This is a k-dimensional volume. So. Okay. Fine. Yes. All right. Okay.
Yeah,
It's fine. Okay. Okay. So that is geometrically what a differential form is. So now, so it gives you a way of measuring infinitesimal k-dimensional volumes. Okay. K-dimensional infinitesimal volumes. All right. So now I'll just come to the definition of integration of a differential form. So first I need to define what is a pullback. So suppose phi is a smooth map from M to N, then we can pull back any omega differential form of degree k on N to get a differential form phi star omega on M. So how is this defined? So phi star omega at a point P acting on vectors V1 to Vk at P is defined to be, you take omega at the point phi of P, let it act on the vectors d phi P V1 up to d phi P Vk. All right. So these will be tangent vectors at phi of P. So omega at phi of P can act on them. Okay. So this is the pullback of a differential form. And okay, so how do we define integrals of differential forms? So first we have to understand what are the right objects to integrate over. So if a differential form of degree k is a way of measuring k-dimensional volumes, you should measure the k-dimensional volume of a k-dimensional object, right? So for example, for a one form, you should measure that applied to one-dimensional objects. What are those? Curves in your manifold, right? So one forms, you should be able to integrate over curves. So suppose omega is a one form and gamma from the interval, say 0, 1 to m is a smooth curve. Then you can define the line integral of omega over gamma to be the integral from 0 to 1 of, so the following function, at each point gamma t on the curve, you look at omega at the point gamma t, apply it to gamma prime t. That gives you a function of t. Now integrate this dt. Okay. So that will give you the integral of omega over gamma. Right. So you can use this, for example, as follows. So if omega is the one form df, right, where f is a smooth function on m, then what is the integral of df over gamma? Well, it's integral from 0 to 1. df at gamma t applied to gamma prime t. Now, by definition, this is the tangent vector gamma prime t applied to f, right? And what is gamma prime t applied to f? By definition, this is ddt of f composed with gamma, right? So then by the chain rule, this is nothing but f gamma 1 minus f gamma 0. Okay. Okay, so by integrating the differential form df over curves, you can recover the function f, right? The fundamental theorem of calculus holds. Okay. Is this all right? Yeah. So we're out of time. So let's continue next Tuesday. If you have any more questions, I can start another session for 5 minutes. If you don't, then I'll stop here. Okay, fine. So let's stop and we'll meet on Tuesday again.